So Unit 3 included circular motion and gravitation, and those fit together nicely because of the orbit type problems, which are circular motion caused by gravity. So first off, the circular motion stuff. We looked at acceleration there to begin with, and oftentimes we'll do uniform circular motion problems where speed is constant. So acceleration is a little tricky there. Speed is constant, and yet it's accelerating. It's just the direction changing instead of the magnitude of velocity. It's just the direction of velocity changing. Fortunately, there's some work done ahead of our time for the geometry on figuring out acceleration in that situation. So we can just do the speed squared divided by the radius of the circle, and that gets us the centripetal acceleration. There's also the idea of acceleration along that circle. It can be getting faster or slower as it goes around that circle as well. We would call that tangential acceleration. There really isn't much of that on the, or really any of that on the AP exam. They wouldn't ask you specifically for tangential acceleration anyway. But just if there is something getting faster or slower, just be aware that that doesn't affect how we calculate centripetal acceleration. The v at that moment squared divided by r is going to be acceleration at that moment. We did not do this in Unit 3. So, okay, skip over that one. We've got Newton's second law again. Just looked at this before. Acceleration is net force over mass. In Unit 2, we did that in the x direction sometimes. We did it in the y direction sometimes. Now we're going to be doing it in the c direction, in the centripetal direction. So acceleration toward the center of the circle is equal to the net force toward the center of the circle divided by the mass of the object that's going around in a circle. So since we know that acceleration is v squared over r, we can combine that with the Newton's second law equation to get v squared over r equals net force toward the center of the circle divided by the mass of the thing going around in the circle. Now, most problems, or most of the time when we do Newton's second law, we get to choose what's positive and what's negative. We could say up is positive, down is negative, or vice versa. That's not the case with centripetal motion. That v squared over r term is acceleration toward the center of the circle, and it always comes out positive. So we have to say toward the center is positive. The net force in the centripetal direction. When you're reading it, just read it that way. The total of the forces in the centripetal direction, or net force in the centripetal direction. I wouldn't start calling that the centripetal force. And certainly don't call it the centrifugal force with a G. Objects don't get new forces solely because they're going around in a circle. So the forces we talked about before, tension and friction and normal force and gravity, those are still the same common forces here. There's no extra force that appears when you turn your car one direction or the other. So that idea of a centrifugal force pushing things toward the outside, it's just wrong in the frame of reference that you guys know how to work with. There is a frame of reference where we have to introduce forces like that, called the non-inertial frame of reference, so an accelerating frame of reference. But even then, we call centrifugal force a fictitious force. It's a force that we recognize isn't really an interaction between two objects. It's just something we have to make up. We have to invent this force because the frame of reference that we've chosen, the motion doesn't make any sense unless we invent a force that isn't really acting on this object. So, long story short, don't do the centrifugal force. And when you read this, just recognize it's the same deal we've done before with net force. We're going to replace that term with forces like tension, gravity, normal force, friction, added together with toward the center being positive forces, away from the center being negative forces. Then we got into gravity. We have this equation to figure out the force of gravity between two objects, called the law of universal gravitation, brought to us by good old Isaac Newton, with G being calculated from that Cavendish experiment. Still a pretty hot issue on my YouTube channel, it turns out. Yeah, it's good stuff. Got a revised version in my head on how we're going to do the next step on that one. I'm sure I'm not going to change the minds of any flat earthers, but at some point it's just kind of fun to point out, oh yeah, look at all these millions of holes in your argument. So anyway, in that equation, g is the gravitational constant. It's not 9.8. So little g is 9.8. Big G is not 9.8. The case on these letters matters. Big G means something different than little g does. Big G is 6.67 times 10 to the negative 11th cubic meters per kilogram second squared. Don't bother memorizing it. It's on the front page of your equation sheet. M1 and M2, the masses of the two objects that are attracting one another. And then R squared, that's the center-to-center distance between those objects. Right now, if you wanted to find the gravitational force between you and the Earth, the center-to-center distance would basically just be the radius of the Earth. I mean, that extra half a meter to your center, that's not going to change the problem significantly. But if we have objects that are, a more significant distance apart from one another, like say the Earth and the Moon, we want to do center-to-center distance, not surface-to-surface on that. Then you might see a little bit. Earth to Moon, and you're probably not going to see a huge difference even if you do it the wrong way, just as a general rule. Definitely when we do things like orbit, we'll see the term altitude. Altitude means the distance above the surface of the Earth or whatever planet. So that isn't the distance that we want to plug in here. That R is not altitude. So we need to go not only from the satellite to the ground, but also from the ground all the way to the center of the Earth. So you need to be careful on those. Gravitational field describes this change in space that happens because of a nearby mass. So when we look at that, that spandex sheet analogy or the bowling ball on a trampoline analogy, the idea is that just putting the bowling ball on the trampoline or putting the weight on the sheet, it changes the shape of the sheet. And then a second object that we put on the sheet moves differently because the sheet has a different shape to it, or the bowling ball has a different shape to it. So if you put a bowling ball in the middle of the trampoline, suddenly a marble put on the outside is going to roll toward wherever that bowling ball was. Or if we get it moving to begin with, it's going to curve. It doesn't travel on a straight path. It curves around that bowling ball. So that idea that the trampoline is a different shape now, and that affects the motion of other objects nearby, that's the analogy we make for a gravitational field. The Earth has caused a change in space around the Earth. Space has a different shape, or I don't know, some characteristic to it. Maybe shape isn't even right because we can't see this shape of space that we're occupying. But some property of that space has changed as a result of the Earth's presence. Gravitational field describes how much change we've seen and in which direction. Now, the way we calculate that is just by measuring the gravitational force on some object and dividing by the mass of that object at this location that we're interested in. If we can't measure the force directly, if we can't go there and bring a spring scale at an object of known mass, we could calculate it. We have the equation for gravitational force, so we could calculate the gravitational force acting on that object at that location, and then divide that value by the mass of the object at that location. The gravitational field equation, as we use it most frequently, is just this equation, the gravity force equation, divided by mass. So it's just this equation, except it only has one mass in it instead of two of them. So it's gm over r squared, where m is the mass of the object that's causing that gravitational field, and r is the distance from the center of that object to whatever spot we're interested in. Gravitational field is a property of a location in space. So it's not going to say what's the gravitational field of the Earth, it's going to say what's the gravitational field caused by the Earth at some location. We got to have the location in there. The surface of the Earth, we would get 9.8 for the number on that.
What's the mass in that equation?
The mass of the object that we put at that location to test the gravitational field at that location. So if I had a 1 kilogram mass as my test object and I put it right here on the surface of the Earth, then the mass that goes in there is the mass of that test object, the 1 kilograms, which means in this equation we'd have the mass of the Earth and the 1 kilogram in there. It's the 1 kilogram that gets canceled out. Only the mass of the Earth ends up staying in that equation.
Did you say little g is equal to big G times mass over radius of Earth? If you combine them, I mean.
Yes.
Okay.
Yep. little g is equal to big G times the mass of the object causing the gravitational field divided by the distance from that location to the center of that object squared.
M is the mass of the object causing the field.
Yes.
Not the one that's affected by the field.
Right, right. Okay, and then the last thing that we did, or I don't know, the middle thing that we did actually, was orbital motion. These are out of order, I guess. Orbital motion we'll think of as circular motion. Often orbit isn't quite circular, but for things like planets and moons, it's often very close to being circular. Circular motion, where the force toward the center of the circle, the force in the centripetal direction, is a gravitational force. On the AP exam, they don't give us orbital motion equations. They expect us to know that orbit is circular motion and gravity happening simultaneously, and so we can take an equation for circular motion and an equation for gravity and put those two together. That's the conceptual understanding that they're testing by not giving us those derived equations from that. So here the arrows show that we substitute these two equations. We put these two equations together. The force toward the center of the circle is the gravitational force. So if I replace that net force in the centripetal direction term with big G m1 m2 over r squared, then I can get an equation for orbit. V squared over r equals the force big G m1 m2 over r squared divided by m. And remember, in that first equation, the orbital motion, the circular motion equation, the m that's in there is the mass of the object that's going around in the circle. So when I divide that gravitational force equation with both masses by m, the m that gets canceled is the mass of the thing that's going around in the circle. We're left in this last equation, v squared equals gm over r, we're left with just a single m. That's the one that didn't get canceled out, which is the one that's not going around in the circle. So the thing that's at the center, if we have a satellite orbiting the Earth, the mass in that equation is the mass of the Earth. If we're talking about a planet orbiting the Sun, the mass in that equation is the mass of the Sun. It's the central object. That determines orbital motion, not the mass of the object that's going around. That's completely inconsequential. All objects, regardless of mass, would orbit the same way given the same distance away from that center object. The last thing that we did with this, we also said v can be set equal to distance over time. Speed is distance over time. And the distance that we're talking about is the distance to go around this big circular path once. So the distance around a circle is the circumference, 2 pi r. The time to go around once is just a time that we call the period, the orbital period. So we can make one last substitution here. Instead of v, we can put in 2 pi r divided by t. 2 times pi times r is the distance, and t is the time divided by time. So distance over time, that's speed. So we can do one extra substitution and we get rid of speed, and instead we have a t in there, the time to go around once. So then we're relating the distance from that central object and the mass of that central object to the time it would take an object to orbit once. So that'd be an orbital period equation for orbital motion. But again, not given to us on the AP exam. They expect us to get conceptually that we can combine these two ideas, circular motion and gravity, and then that means we can also combine these two equations.
And for your response question, could you just list that bottom equation in the blue box? Or
Nope.
would you have to show all that work?
On a free response question involving orbit, they'll have a point associated for recognizing that this is circular motion, and you can recognize that by doing v squared over r equals net force over mass. They'll have a separate point for recognizing that that gravitational force equation is relevant, and then probably a third point for doing a substitution that combines those two. So starting out with v squared equals gm over r, you may get to the right answer, but those beginning points for showing your thinking there you would miss out on. Yeah. Other questions on the circular motion or gravitation stuff? Okay, cool. So that's all the content. We can do some practice then until 5:15. We got about 25 minutes.